For some reason, the company is unknown because we don't sell our products in our brand name, but Nokia does or someone else does. But the heart of all the chips will be, or the products will be our chips. So there was a talk from Alok, Mr. Alok earlier on the RTL to GES flow and stuff, where I will be now talking about a small part called timing, and in that also one small part called CDC, that is clock domain crossing. He was mentioning that the clocking is very important in any design, right? That's what will make any chip timing closed, or which will make any chip successful, or it will make the, it will work fine or whatever it is based on the clock. That's what he mentioned. So now, as the technologies are increasing, the requirements are increasing by day-to-day life, right? The chip sizes are also going higher and higher. We are talking about the technology shrink, but it's not happening on the chip size. The chip size is going on, increasing and increasing. Because we are stuffing more and more, requirements or the specification to single chip. So which are increasing actually the size. Now when the chip size increases, the clocking or the CTS becomes more tougher and tougher. Because you have a whole bigger area. The CTS is something in very small definition, if I want to say. We have to make the clock reach every flip-flops that is in the design at the same time. This is the ideal definition that we say. There is a huge problem if the clock reaches at the same time to the whole chip. That's a different discussion altogether. But when we say with some delta, very minimal delta, if all the flops needs to get the clock at the proper time, then how do we do it? Yes, we do have tools, but when we talk about tools, currently the chip sizes are of, let's say, 15 cross 15, 15 mm, when I talk, which is very huge. And to do the CTS for particular 15 cross 15 mm size, one single tool or one single run, it cannot be done. It will run for months. The runtime will be of months together. It will at least run for 30 to 40 days if you want to run it. Now what we do is basically divide and rule. We divide into all the sub-logs, and then we do the CTS, then we club and we call it as a chip level and stuff. Now when we do that, what happens is there might be some clocks or some blocks which are working at 200 MHz and some are working at 400 MHz, or some might be in different frequency, because all the logic need not work at the same frequency. That is not the need of the chip or need of the logic. Now when we have these kind of different frequencies in a single chip, and when two logics working at different frequencies interact, that's where we call as clock domain crossing. That is from a clock A domain to the clock B domain, there is a data transfer. And how do we take care of it is the concept that we had to discuss. I am coming to a last part where the timing closure. How do we close the timing? How do we sign off a CDC part is where I want to talk. So, for some reason it's cutting my part of the slide. So, this is the ideal circuit that we can call single clock circuit. The whole chip has a single clock and one frequency, and it's very straightforward. Everything is easy here. But as I mentioned, the complexity of the SOCs are increasing day by day. Single frequency or single clock circuits are very rare these days in the industry. There are chips which are very, very small, But when we go for bigger size of SOCs and stuff, there are no single clock circuits. It's all multiple clock. So now, when I say clock domain, I will be using more and more of this term called clock domain, right? So I have mentioned few diagrams here, right? It's something like one particular clock is driving a few set of cells, right? Or few set of instances or flops. That particular flops or that particular set of instances are called a domain. It is nothing but you can call it an island where, okay, the clock is going to these many cells. Let's say I have 1000 cells or 1000 flops in my design, and I have 10 clocks. And I say 100 flops are getting clock A, 100 flops are getting clock B. So clock A domain is these 100 flops. That is the simple definition for clock domain that I can see. Now, the CDC can happen, the clock domain processing can happen in two ways. One is, let's say you have 3 clocks in your design, clock A, B and C. Clock A is 50 megahertz, clock B is also 50 megahertz, but clock C is 75 megahertz. Okay. Now, clock A to clock B domain, there can be a data transfer, which is straightforward, 50 megahertz to 50 megahertz. But clock A and B to clock C domain, that is something tricky here, because 50 megahertz to 75 megahertz, it's not the same frequency. So the phases will not match, right? The setup and hold time calculation will not be that straightforward here. This is where the CDC concept itself comes into picture now. Now, we can say why there might be 2 clocks of same frequency in the design. It is basically to control one particular set of instances that we might need, and another particular set of instances that we don't need for one particular operation. And for another particular operation, we need both the designs, right? Both the logics. In such cases, we use 2 clocks of same frequency, sometimes generated from the same PLL and stuff. Sometimes it is different, it is all driven by the architecture and other things, right? So if, let me take the example here, one example where, one clock A is 50 megahertz and clock B is 37 megahertz. Now if we at all we draw the waveform for 50 and 37 megahertz, we will never be able to match the rising and falling edge of the clocks, which we call as out of phase clocks, right? 50 megahertz and 100 megahertz clock, if you write the waveform, there might be some phases that will be matching, right? In industry we call it as asynchronous clocks. Those will not become asynchronous unless you define it, right? For some particular corner case we might define it, right? Now here it is a clear case that the phase will not match. Now let's say flip-flop A is getting clock A and B is getting clock B, and at the positive edge FFA is launching some data. We never know in the real world when the positive edge of the clock B will come. So the capturing of the data at the next flop is a mess here, right? Let's say we have some important data that is coming at A, the data path A. That will be missed out, or that might corrupt the whole system. Because the data will keep transferring from one flop to the other flop, right? It doesn't have, so much intelligence to say, okay, whether should I, okay, the data is not proper, I will not send it. It doesn't do that. It gets something, it transfers it at the next positive edge or negative edge. depending on the flop type.